Hi everyone, thank you for coming. My name is Sean Liu, and today I'm going to talk about our work, ZoomShop, Depth-Aware Editing of Photographic Composition. This is joint work with Manish Agarwala from Stanford, as well as Stephen DeVerde and Aaron Hertzman from Adobe Research. Many of us can probably relate to the following problem. We see the moon in the sky, take out our phones, and take a picture. However, the moon appears much smaller in the photo than it does in real life. Well, this turns out to be an instance of a larger problem, where linear perspective photographs may not fully capture subjective visual experience. And this phenomenon is also observed by perception scientists and artists. In this project, one of our goals is to resize objects in photographs, which could be useful for better conveying scenes and describing visual experiences. For example, in this photo, I might think that the lighthouse looks smaller than it does in real life and want to enlarge it. But if I simply zoom in and crop, I would ruin the original framing and composition. In particular, this ridge in the foreground would be cut out. In the original image, the ridge served as an important compositional element that framed and balanced the whole image. Ideally, I would like something that looks like this, where the lighthouse is larger, but the ridge is still fixed in place. We've created a tool called ZoomShop, which can achieve this. But first, why is this a difficult problem? You might think we can cut out the lighthouse, resize it, and paste it back in. However, as you can see, doing this manually in Photoshop can be pretty tedious. And even though it might be easy for an expert user, in general, this is not a trivial problem. Consider this more complicated scene. Suppose I want to enlarge this building while keeping the boat in place for composition. Because there are more surrounding objects, this task becomes more difficult. If we zoom in here, you can see that there are boats on the right, more buildings on the left, and pillars in front. All of these add more constraints to the problem. Specifically, there are two types of constraints. The first constraint is to maintain depth continuity. When we resize the building, it needs to be attached to the ground. The second one is to preserve depth ordering. Things in front of the building should stay in front, which means we should not include the boats on the right, the poles in front, or the buildings on the left, which are at the same depth as the main building. In summary, we want some sort of scene depth understanding to preserve depth structures in the image, and simply cutting and pasting does not work well in general. At a high level, here are our goals for editing photographic composition. First, we want to make some target object appear larger or closer. In this example, the target object would be this building. Second, we want to maintain scene element visibility. In this case, it would be the boat on the left. And finally, we want to maintain scene element spatial relationships, which include depth continuity and depth ordering. Here are some related works. There are many image retargeting techniques which are very powerful. However, many of them do not consider depth and thus may not preserve depth structures. Perspective deformation techniques are also powerful, but do not support changes in occlusion relationships. This limits how much they can deform foreground and background elements differently. Other techniques use estimated depth to reproject an image, but because they use linear perspective, their model cannot enlarge a distant object while keeping some foreground element fixed. There are also many general-purpose camera models for creating multi-perspective projections. Our approach includes a nonlinear camera model, which is most closely related to Computational Zoom, proposed by Bodke et al. However, we use a more flexible parameterization and support a wider range of edits. I will revisit Computational Zoom later with a more detailed comparison. At a high level, our approach is to use depth information for editing and warping photographs. We assume we have depth information available, or we obtain them as a pre-processing step. This is a reasonable assumption given that many consumer mobile phones have built-in depth estimation, and computer vision techniques for depth estimation are improving rapidly. With that said, here's a high-level overview of our approach. We break this problem into two subproblems. In part one, we work on editing objects at different depths. And in part 2, we look at editing objects at the same depth. In part 1, we allow users to adjust the scale of objects at different depths by defining a new nonlinear camera model. This camera model helps preserve depth structures during edits, and I will go into more details of this shortly. In part 2, we look at editing objects at the same depth. After scaling, some objects might get pushed out of view, such as the two side hills in this example. To maintain visibility, we apply a depth-aware warp to translate them back into view. Before we dive into the details, we highlight the contributions of this work. First, we show that it is a worthwhile task to adjust object size, foreshortening, and position. From the motivating examples, we can see that it is often desirable and useful to make these types of compositional edits. Second, we propose an approach for achieving these edits by combining a new nonlinear camera model with a depth-aware warp. As part of our approach, we define a new camera model parameterization, which enables user controls specifically designed for ease of editing and maintaining spatial relationships. And finally, we want to highlight that our contribution is the alignment between the user controls and the underlying implementation, not the user interface, which may have limitations. And with that, let's take a closer look at part 1. In this part, we start off with an image, obtain a depth map from an off-the-shelf model, and construct a 3D scene using the depth map. Shown here is a top-down view of the reconstructed 3D scene. At first, we just use conventional linear perspective, where the boundary of the view volume is shown in red. As users make modifications to the image, their edits are mapped to edits of the view volume boundary, which is no longer linear. We then reproject the scene under this modified view volume. Disoccluded and sheared pixels are shown in cyan. And finally, users can export the image and inpaint the cyan pixels using a tool such as Photoshop. And next, I'm going to talk about our camera model in more detail. Here's a quick recap of linear perspective. This is a top-down view of a camera frustum. Given a scene point in 3D space, we project it to the image plane by drawing a line from the scene point to the center of projection. Things outside of this boundary, such as the yellow dot, are not visible to the camera, but things within the boundary, such as the green dot, are visible. We can parameterize the view volume with this boundary curve, B of z. We assume a symmetrical view volume, so we can just focus on the top boundary. The bottom boundary is represented by negative B of z. In linear perspective, B of z is just a linear function over z, where c is a constant. But we can also use nonlinear curves for the boundary, which provides more power for editing photographs. To show this, I will walk through an illustrative example. Suppose we have the scene with the foreground and a background element. In the lighthouse example, we can think of the ridge as the yellow rectangle and the lighthouse as the green rectangle. To enlarge the lighthouse using only linear perspective, we can zoom in and crop. This is equivalent to making the boundary narrower at the depth of the lighthouse. However, this approach also cuts out part of the ridge in the foreground. Instead of being constrained to linear boundaries, we can use nonlinear ones to keep the ridge in view. For example, we could divide up the scene into two depth regions, one including the ridge and one including the lighthouse. We can then use different boundary segments for these two regions so that the ridge is fully in view while the lighthouse is enlarged. This is what the output looks like with the piecewise linear boundary. As you can see, B of z is inversely related to the scale of objects. In this example, we made B of z smaller at the lighthouse, which enlarged it on the image plane. If instead we used a larger B of z at the lighthouse, we get a smaller lighthouse in the image. In summary, this B of z parameterization offers flexible user controls and is very powerful at editing photographic composition. In this example, we only used two depth regions, but in theory, we could divide the scene into many more regions. And in general, the boundary could be a curve instead of a piecewise linear function. And in ZoomShop, we support linear, piecewise linear, and curved segments for editing photographs. And specifically, we map user edits to edits of the boundary curve, and then use the new boundary curve to reproject the scene. In ZoomShop, users can adjust scale and foreshortening of different depth regions. As shown before, scale is inversely related to BFZ. We can also use BFZ to adjust foreshortening, which is directly related to the slope. And I will walk through an example of each. First, let's take a closer look at changing scale. Here's the lighthouse example again. The user only sees the image on the left. Note that the boundary curve is a parameterization that is only used by the system and is not exposed to the user. The right shows a top-down view of the scene and is for visualization purposes only. First, the user selects the lighthouse by clicking on it and adjusting the front and back depth planes. On the right, you can see that ZoomShop creates a new BFZ segment for the lighthouse region. Next, the user increases the scale of the lighthouse. To achieve this, on the right, you can see that ZoomShop decreases the green BFZ segment. After enlarging the lighthouse, the user realizes the ridge is partially cut out and wants to keep it in view. So the user selects the ridge and adjusts the front and back planes again. This creates another BFZ segment in ZoomShop, shown in green. As the user decreases the size of the ridge, ZoomShop increases BFZ at that depth. Here's a before and after comparison side by side. Disoccluded and sheared pixels are shown in cyan, and users can inpaint these pixels later to get the final image. Next, I will walk through an example of adjusting foreshortening, which is directly related to the slope of BC. In this example, the user thinks the bridge appears more compressed in real life than in the image, so they want to decrease the foreshortening of the bridge. To do so, the user first again selects the bridge and adjusts the front and back planes. Next, as the user decreases the foreshortening, ZoomShop decreases the slope of BC. Here's a before and after comparison. The effect of decreasing foreshortening is that the bridge appears more compressed in depth. And you might notice that by making this change, the church in the background is also brought closer. And next, I will talk about some properties of the boundary curve. You may have noticed that so far in the examples, the BZs have been continuous. Using a continuous BZ means depth continuity is preserved. However, in some cases, we may want to add discontinuities for more powerful edits. For example, in this scene, we have the Eiffel Tower in the distance and a gargoyle statue in the foreground. We can enlarge the Eiffel Tower while keeping the gargoyle in place by using this boundary curve. Notice that at the depth of discontinuity in the curve, the ground also becomes discontinuous. By allowing for discontinuities, users can make the Eiffel Tower even larger than if they were constrained to continuous curves. In addition, users can strategically choose where to place these discontinuities, for example, in a textured region for easier inpainting. In this scene, we place the discontinuity where the buildings are, which we can easily inpaint. In ZoomShop, users can choose between using a smooth or linear interpolant to connect edited depth regions. On the left, we use a smooth interpolant to connect the ridge and the lighthouse. Because a smooth interpolant smoothly transitions scale across depth, the road bends smoothly at the circled position. However, if we use the linear interpolant on the right, we can see that there's an artifact where the road bends suddenly. Although smooth transitions are good for some scenes, in other scenes there might be straight lines to preserve, in which case a linear interpolant is preferable. In this example, we see a lawn stretched out in front of Versailles. On the left, we see that a smooth interpolant curves the lawn, which is undesirable. On the right, using a linear interpolant can preserve the straight lines of the lawn. Because the best interpolant to use is scene dependent, we leave it up to the user to select which one they want to use. Circling back to related works, most closely related to our camera model is Computational Zoom, proposed by Bodke et al. Computational Zoom reconstructs a 3D scene from a stack of images, and then uses a piecewise linear camera model for image reprojection. We show that computational zoom is equivalent to a piecewise linear BFZ curve, and we generalize it to curved, discontinuous, and even non-monotonic segments. Our new BFZ parameterization is more flexible and supports a wider range of depth-based manipulations. We also use a simpler workflow by relying on a single image with a measured or estimated depth map, as opposed to multiple images. This enables dynamic scenes and historical events where it might be difficult or impossible to gather additional photos. So that's it with part 1. In part 2, we look at editing objects at the same depth. In this example, we want to enlarge the 2 side hills, marked in green. With just the camera model, all scene points at the same depth get scaled by the same amount. This causes the side hills to get pushed out of view after scaling. Thus, we want the ability to translate them back into view. To do this, we apply a depth-aware rubber sheet warp where we maintain depth structure during translation. Given an image, the user inputs translation constraints in the form of rectangular pairs. We want the magenta rectangles to translate to the position of the blue rectangles. Our goal is to solve for a per pixel translation map that satisfies these constraints. To do so, we formulate this as an optimization problem, where rectangular pairs are converted to hard constraints in the optimization. The objective function includes a smoothness term, which encourages translations to vary smoothly across the image and at continuous depths. The objective function also includes a regularization energy term, which tries to find the smallest deformation that satisfies the user input. Finally, we include a lambda term, which balances the 2 energies and determines how quickly the translations fall off across the image. Here are the results after running the optimization and applying the per pixel translation map. Now we show some more results. In these examples, we will show the original input and the final inpainted output. Note that inpainting is not part of ZoomShop. In our results, we used Photoshop's content-aware fill for inpainting. On the left is the lighthouse example again. We can scale up the lighthouse while keeping the ridge in place. On the right is the Venice example. We can scale up the distant building while keeping the boat fixed for compositional reasons. On the left, we have a boat in the middle of a lake. Using ZoomShop, we can enlarge the boat while keeping the framing of the foreground trees and shore. And on the right, we can enlarge the Eiffel Tower while keeping the gargoyle in place to preserve the context of where this photo was taken. Here are some examples of adjusting foreshortening. On the left, we decrease the foreshortening of the bridge to compress its depth. On the right, we increase the foreshortening of the steps to expand its depth and create a more dramatic effect. Now we show some examples of applying translation. On the left, we decrease foreshortening of the Yosemite Valley to compress its depth, and then we move the side mountains back into view for framing. On the top right, we scale up the Buddha statue and translate the tower on the left back into view. And on the bottom right, we scale up the birds on the float and translate the rock back into view. For our results, we used Midas to obtain an estimated depth map, and for inpainting, we used Photoshop's content-aware fill. In many cases, we had to manually correct errors in the depth maps and provide manual guidance for inpainting. We give more details of this in the paper. Although some manual effort was necessary, we emphasize that depth estimation and inpainting are rapidly advancing fields, and we are optimistic that they will improve in the coming years. We want to highlight that our contribution is not in either of these domains. Rather, our focus is on creating a method for editing composition and providing helpful user controls. And finally, some limitations of our work. First, the translation optimization is not real time. We intended it to be a post-process step after users finish adjusting the scale and foreshortening of the scene. And second, ZoomShop does not automatically preserve straight lines. We leave it up to the user to use a linear interpolant for those regions where straight lines must be preserved. Future work could find ways to automatically preserve straight lines, regardless of the boundary curve. And future work can investigate ways to automatically determine salient depth ranges and recommend boundary curves to the user. There are two main takeaways I hope you get from this presentation. First, as depth information is becoming more readily available, depth-aware editing is also becoming more feasible. Scene depth understanding can help us develop methods to preserve depth structures, which are important for editing composition. And second, we introduced a flexible camera model parameterization, BFZ, which can be used to achieve a wide range of photographic compositional edits. And finally, I would like to thank the photographers who let us use their photos, and thank you for listening.